This is a supplemental video on spring force and the basics of classical mechanics and the elasticity of materials units. We had looked at spring force in a prior lesson, and what we know is that a spring exerts an opposing restorative force in response to an applied force that compresses or stretches the spring from its original length. And we're looking at linear displacement and linear forces. It is true when you think about really stretching or compressing a material, you may apply a stress that is way beyond what that material can handle and restore back to its original geometry. And that's what this graph represents, which I borrowed from OpenStax. There is a region over which the response of the spring is linear to the force being applied. And you can see that. Here's the force applied, here's the stretch in the spring, and it is linear. There's an elastic region where at some point it's not as linear, and then beyond that you can have a permanent deformation, or actually you can see fracture of the material if you deform it past what those bonds in the material can take. So what we're looking at is we're going to assume an ideal spring in all of our problems, which means that there's going to be a linear relationship between this displacement and the force. We've looked at the direction of the spring force. We know that it will be restorative. So if you pull outward in the positive x direction, the force will be inward. Or if you push inward, the force will be outward. Any signs that you come about in the problems, and we're going to be doing force analysis, will come about because you've assigned a coordinate system. The spring force in quantification is known as a vector equation known as Hooke's law. The spring force vector is in the opposite direction and multiplied by the spring constant k times the displacement vector. And this arises through Young's modulus. We know that a force is applied over an area and it causes a change in length over length. I looked at this in a prior lesson where we saw that the force being applied is YA over L times delta L. And you can see how this equation copies that. And what we're saying is that the YA over L, the Young's modulus, area and length, is a constant value that we can call K. So then it's related to the force and the change in length, which we call delta X in Hooke's law. I don't prefer this form of the equation in order to solve problems. I actually prefer the magnitude equation, and that's what I put up here, magnitude, where I just have a positive value and any sign comes about because of an assigned coordinate system. We're going to be doing force analysis. You will be asked to do free body diagrams and assign a coordinate system, and that's where the signs will come into account. I don't generally use this form unless it's in concept. When you draw your spring force in your free body diagram, you're already taking into account this negative sign by drawing that direction. So you don't need to take into account that negative sign a second time in your equations when you set up your force analysis. I just wanted to clarify that as we move forward so that you are able to do force analysis well. The problem I've chosen is a pretty clever question, and it relates to the lab for this material. A spring has length 20 centimeters when a 425 gram mass hangs from it, and a length of 35 centimeters when a 565 gram mass hangs from it. So there's an original situation. There's a length of spring, and it has some original L naught, and that's what you see in the equation, L naught here. When a mass is applied to this, it gets stretched out, and I'm going to actually draw it so that the springs are a little bit farther apart, so then it's stretched out. It has this new length, L1, which I will call it, and it's because M1 has been put on the end of it. So we have this new length, L1 will be larger than L naught. We have another situation where it's even more stretched out. So I'll go like this. So we see that it's a longer length, and this will be L2. And that arises because M2 was put on the end to it. And M1 is smaller than M2. You can see that there's the stretching going on. So that's sort of the situation we're looking at. It says, what is the force constant of the spring? So they're asking us to find K. And what is the unloaded length of the spring? So they want us to find L naught. What is L naught? We know that L1 is 0.2. I'm going to convert this to meters. We have 0.2. In the second situation, L2 is 0.35. In the first situation, M1, I'm going to put this in kilograms. M1 is 0.425 kilograms. And in the second situation, this will be 0.565 kilograms. When I look at the situation, I want to do a force analysis. So I'm going to draw a free body diagram of a mass, and this could be the mass in either situation. I'm going to have a spring force upward, which is responding to the weight, which is equal to mg downward. And this is true in two different situations. I can assign a coordinate system upward, positive x, and apply Newton's second law, the net force equals mass times acceleration. I know that there's zero acceleration. These masses are just sitting there. And so the net force on it is going to be the spring force upward minus the weight down, and I'm just going to put what I know in there. The spring force is K delta x. I don't have to worry about the negative sign because I already took the sign into account when I drew it upwards. So what this equation tells me is that K delta x equals mg. And what I could even do is plug in what I know about delta x. So in each situation, I know that there's a K, L minus L naught, and that equals mg. So in the first situation, I have K equals 0.2 minus L naught, which equals M1, which is 0.425 G. And in the second situation, I have the very similar equation, except I'm replacing the length. It has a new length, and it has a new mass. Okay, so we're golden here. There's two equations and two unknowns, and you're welcome to solve the problem with this, just setting up those two equations and doing some algebra on it. However, I want to highlight the clever way to solve this problem is to realize that this is a linear situation. This is linear. So whatever force is being applied, then it responds linearly, the spring responds linearly in displacement. And if I'm trying to find a spring constant, and this is what we're going to do in lab, if I want to find the spring constant, I know the units on the spring constant are newtons per meter. And so if I think about these two sets of information as being 2 points on a coordinate system, where I have force on the vertical axis and L on the other axis, I can put in these points. I can put in the length is 0.2 and the force is the gravitational force, the weight of 0.25 kilograms. And then it increases in length and increases in force, and I have the equation of a line. Those are my 2 points, 0.1 and 0.2, and they're connected by a line. And actually, the slope of this line will be the K value because I did force over length, right? The slope will be the change in the vertical over the change in the horizontal, newtons per meter. So all I have to do to find K is to find the slope of this line. I'm going to define my 2 points. The first term is the L. So in the first situation, I have 20 centimeters. I'm going to put 0.2 in here, and the force being applied is, remember, this is going to be the weight. So I'm going to put 0.425 times gravity in there. So that's my first point, and my second point is going to be 0.35 and then 0.565 G. When I do K equals change in the force over change in the length, I will get 5.565 G minus 0.425 G, and I'm going to factor G out right there, divided by 0.35 minus 0.20. All right, This is going to give me the K value right away. Like I said, you could do your algebra and do plug and chug and two equations, two unknowns here. But when you recognize this is really powerful, that it's a linear relationship. I'm just finding the slope of this line, and that will be the K value. And you get, when you run this through the calculator, 91.46 repeating, which I'm going to round off at that, and the units are newtons per meter. And there's the K value for part A. Part B is fairly simple. Once I know K, I can plug it into one of these equations. Just plug it back into one of the original equations and solve, which means that I need to solve one of these equations for L naught. I'm going to use the first or top equation up here. I'm going to divide by K on both sides and rearrange my L naught in that term. So I'm going to get 0.2 minus 0.425 G divided by the K value, 91.46 repeating. When you run that through your calculator, you get 0.1545 meters, or 15.45 centimeters. And I convert it to centimeters because I'm interested in comparing it to the original length. I definitely want this number less than 20 centimeters, and that's what I got. So when M1 was applied, it stretched out a little bit less than 5 centimeters, and when M2 was applied, it stretched out a little bit less than 20 centimeters.